All right, my name's Shaddy, and today I'm going to be talking about building Dissent networks. And this is some joint work that I've done with my colleagues, Helman David, Julia Fonte, Eric Brewer, and Scott Schenker, and all of us are over at UC Berkeley. So the problem we're talking about today are large-scale communications blackouts. And as most of you will remember, in 2011, Egypt shut the whole country off the internet. And this is a graph reminding us they did it all in 30 minutes. And while this was kind of an unthinkable event at the time because of all the collateral damage inflicted, other countries have carried out similar actions in the years since, most notably Syria just this summer. And so since 2011, there's been a lot of interest in building tools to circumvent these blackout events from a bunch of organizations, including the State Department. And the motivation for our work grew out of the interest that my co-authors and I have in this space, but also our concern with some of the leading proposals, the leading proposed solutions. So what we're going to try to do today is provide a critical look at those proposals and attempt to start a discussion on design imperatives for people who are trying to build these large-scale blackout circumvention systems. So to kind of frame the discussion a bit, what we're talking about is communications infrastructure for dissidents that exists in-country communication. It's not getting videos out. We need to build alternate physical infrastructure when our internet connection has been cut off. And so we're talking about things like Commotion, Serval, Freedom Tower, etc., which are actually projects targeted towards building alternative infrastructure as opposed to Tor or VPNs or whatever that only work if you already have an existing internet connection. So let's put ourselves in the shoes now of someone who's in Egypt in January 2011 and the internet's just been cut off. So what are we going to do now? There's lots of things we could do. Arguably, the right one is take to the streets and demand political change, but we're all technologists here. We like to build our way out of problems. So I'm sure some of you are thinking, let's go about building a mesh network. Some of you are also thinking, I didn't realize that was still a thing. I thought that went away, but as of last week, it is still a thing. And for those who don't know what mesh networks are, why we might want to build them, they're basically these infrastructure-free networks that consist of a bunch of wireless devices, usually with directional antennas. We call the devices nodes. And they have this really nice property that they are self-healing and self-forming. We have these routing protocols that figure out the right way to connect all these nodes together, and they automatically make paths to the network so we can communicate. It has this nice property where if one node gets taken over by an evil spy or gets blown up and goes away, we can just route around the damage, and everything's hunky-dory. So if we want to build this network, we have to ask ourselves a few questions. First off, how's it going to grow? We have a couple of choices here. For traditional networks, we plan their growth. We figure out where we're going to put new devices, how we're going to connect them, are we going to line up antennas in a certain way. But with mesh networks, because of this self-forming property, we can also let them grow organically. So we can just distribute nodes as we're able to, and the network will just form itself, and it can grow organically. The next question is how we're going to manage it. Again, traditional networks typically have a single person or a group of people who make decisions for the whole network, about network policy, how they fix when things break, how it gets fixed. But in a mesh network, the infrastructure is completely distributed. It could be distributed over multiple people. So we can actually have different people who are in charge of different parts of the network making their own decisions independently. And finally, we have to decide what the topology of the network is going to be like. Is it going to be a static? Are all the nodes going to be stationary? Or are we going to allow for infrastructure nodes that move around like mobile phones? And I want to emphasize that you can pick any point in this whole design space and build a mesh network, and people have done it. There's examples of all of these. But if we're activists, then we probably want to have the properties of organic growth, decentralized management, and mobile topology. Simply because that seems like it's going to be harder to shut down. Our government adversary, on the other hand, has already proven its ability to shut down planned centralized networks. They shut off the internet after all. So, in thinking about this, this is the contribution of our work. We're trying to outline these design imperatives for people who are building these systems. And I think these kind of come out of our thinking on what it means to build a successful mesh network. And so we call these Dissent networks. They need to be resilient to disruption, obviously, because that's the whole point of what we're trying to build. But more than that, they need to have meaningful scalability properties. If we're in a revolution environment, opportunity costs matter. And more than that, we have lots of other options for communicating with our activist friends. Megaphones are surprisingly good tools for communicating over our local area. when we're actually putting together the equipment for this network, we're going to have to stage it beforehand, or we're going to have to somehow scrounge together the equipment once the revolution's already started. So the components need to be innocuous. They can't get us in trouble. We're already taking a risk by building this thing. We should try to minimize that. And finally, these networks need to resist tracking. We don't want to provide another mechanism for the government to track us. So, if the first objective was the only one, mesh networks might make sense. But unfortunately, they failed to meet some other criteria. So I'm just going to walk through some of those reasons right now. And the core one is this. It comes from a really foundational result from 2000 paper by Gupta and Kumar about the capacity of wireless networks. And basically what it shows is as you add nodes to a mesh network, the capacity available to each node approaches 0. So it actually gets worse as the network grows. And they even provide the helpful advice that perhaps we should target efforts at designing small networks to get around this problem. But it's not just a theoretical problem. More than that, in 2001, Junyan Lee and her colleagues at MIT actually validated some of this result experimentally with simulations. And one of the many experiments in their paper is this one, where if you imagine your mesh network to be a big chain of nodes, where each node can communicate only with its neighbors, as you increase the length of the train, the throughput that you get through the chain actually drops off significantly. It gets worse as the network gets larger. So, there's like an obvious result from this. Maybe we can't use mesh networks to send large files. Sure. But maybe small things will work. And that turns out not to be the case either. Because the fundamental reason for these poor scaling properties is channel contention. So let's walk through posting a tweet. Right, we have this nice 9-node mesh network. Our tweet fits in a single packet, and we're going to get a single packet back in response. So we're using omnidirectional antennas, as most mesh networks do, in order to increase resilience. Our node A is going to transmit to all its neighbors, and node B is going to receive an identical radiation pattern. It's going to be able to receive from any direction as well. That also means it's susceptible to interference from any direction, which is a bad thing. Because in order for our first hop, or our first wireless hop to succeed, no other nodes can be transmitting at the same time. If they are, it will fail. We'll have to retransmit. Similarly for the second hop, and we have an identical problem for the response in both directions. Now, obviously, this is not how real networks work. You have to set up a TCP connection first. That's another wireless round trip. If you want to do something over SSL, that's 2 more at least. So we're talking about a minimum of 4 round trips for each tweet that we want to send. We want to send more tweets. It gets worse and worse. So things fall apart pretty quickly. And so, I'm glossing over some details, and it's possible to build networks that get larger. You can do things to get around the Gupta and Kumar result. You can use directional antennas, or introduce mobility, or have multi-radio nodes to reduce the amount of channel contention you have in the network. But all of these come at a cost, whether it's in terms of resilience, or whether it's just in pure money terms. You can accept the Gupta and Kumar result and incorporate delay tolerance into the applications you're going to run in the network, or just build smaller networks like they actually suggest. But this reduces the efficacy of the network, and also it hurts the user experience if your applications aren't designed for it. Or you can result in central planning and coordinated management to try to mitigate the amount of channel contention you have in your network. But then we're back to building networks that are easy for the government to shut down. So, okay, we tried to build this basic mesh network, it didn't work. But maybe there's some practical modifications that we can make. Or maybe there are other systems we can use. First one that comes to mind are satellite. And the great thing about satellite networks is they're really easy to deploy. You just point it up to the sky, and it works. We know it works. Journalists use these all the time. Military use them all the time. Many of you have used these. But as anyone who has used them know, satellite internet access is expensive, and it's slow. Moreover, the equipment for the client equipment you need is not exactly in every electronic shop in every corner. It's hard to source. And in some countries, it's illegal to even operate without registration. And more than that, it's easy to trace and jam. And so from a technical perspective, you can probably get around some of these drawbacks, but you're still going to build this system that's not going to scale to the large numbers that we really want without spending a lot of money or doing something. So what we really want is maybe something like an internet in a suitcase that we can just open up and we get internet access. And this reminds us kind of our second, or rather our third criteria about using innocuous components. So there's a few things in here that look pretty normal. No one may know what the CD is anymore. but everything else you'd expect to find in someone's apartment. These are, Wi-Fi radios. They look a little weird, but they're actually pretty common throughout the world. But where we start to run into problems is when you have, these other two components. When was the last time that you saw someone with a sector antenna that wasn't a cell phone tower? And speaking of cell phone towers, there's been proposals to run pirate cellular networks by activists. And this is just a bad idea all around, because in every country on Earth, with the exception of the Netherlands, operating an unlicensed or unauthorized cell phone network is going to get you in a lot of trouble. Stay away from it. And even if we're not talking about illegal equipment necessarily, legal stuff can still get you in trouble. One of my co-authors, Yahel, founded this great organization called Airjaldi. And what it builds is, wireless networks throughout India. Started in northern India in Dharamsala. And basically, when they started out, they, within a few years, built what was the largest wireless mesh network in Asia, probably in the world. And this picture is of one of their towers. Everything about it is 100% legal. But Yahel's actually been arrested under suspicion of espionage for going around and setting these up in people's rooms. They just look weird. They're going to get you in trouble. They're very conspicuous. So maybe you can find a way around this too. Let's say we actually successfully build one of these networks. What about anonymity? I was told to say federal employees should close their eyes. As we all know, once you build an effective network, the government's going to want to attack it. It's a really valuable resource for an adversary. They can use it to gather intelligence. They can use it to figure out social connections between activists. They can use it to infiltrate and spread misinformation. And all of the things that we want to prevent. However, some of these problems are questions of communication secrecy. We can solve some of it with encryption, but we really contend that Dissent networks should also think about anonymity in their design. And I want to, just say up front, we don't have an answer to this. We're not. It's a hard problem. We aren't proposing a solution here, but it's a design criteria that we haven't seen discussed enough in any of the leading solutions. So open your eyes, federal employees. So let's talk about ways to keep users safe. One way we can do this is with providing real anonymity guarantees in our wireless, in our networks, whatever we're building. Pseudonymity is insufficient here. We know we can de-anonymize pseudonymous systems. There's attacks in the Bitcoin network, etc. And this is a particular threat, given our adversary is a state. They're going to have lots of external information about us so they can cross-correlate with our network activity. Now the problem, of course, of providing true anonymity in one of these systems is really, really hard to build. And moreover, if you were to provide real anonymity, I'm so much trouble with that word, you're going to lose the ability to provide reputation. Your activists who are using this need to know that they're able to trust information that's coming across the network. So another approach is deniability, and this is, something that we see in other systems. Tor, for instance, there's lots of legitimate uses of Tor. Just because they're using Tor doesn't mean you're taking down the government. And so you can imagine other approaches like Telex uses, where we have traffic that might get us in trouble that we're going to hide inside, innocuous traffic. And this is a nice approach too. There are systems where this works in practice, but it's still kind of sketchy because it's hard to take these concepts of deniability over to building real infrastructure networks where just your participation is incriminated. You set up a node. You had to actively go and do this. That's going to get you in trouble. And moreover, if we're going to have non-activist traffic across our network, that's going to increase load. And if we're already in a resource-constrained environment, that's a bad thing. So the real answer is probably some combination of these, maybe something else. Like I said, we don't have answers. This is a hard problem. So I painted a kind of grim picture here. But we think there's some ways forward. We know how to build systems that protect people's identities really well. Tor is a great example. Dissent's a good example. We're going to hear about some more work this afternoon that's kind of similar to Dissent. And some lessons from this might be able to carry over to circumventing large-scale blockouts. Bless their hearts, Commotion and Serval, they're actually the only ones who are really actively working on this problem in a meaningful way. It's a hard problem, and give them credit for what they're doing. While we don't disagree with their technical decisions, They're building actually really effective social organizations around this problem. They're developing operational experience that's going to produce good lessons for people who are building future blackouts or convention systems. One cool thing actually coming out of Commotion to kind of sidestep the protecting user identity problem they've done is they have these privacy warning labels when you download their software. So rather than actually solving a lot of the security problems associated with the networks they're building, they're trying to be transparent about the limitations of them, and in the hopes that users can take actions that won't, get them in trouble. And kind of a plug for my co-authors, they're working on this cool project called Rangzen, which is going to incorporate some interesting lessons from the delay-tolerant networking community with a system for providing a notion of reputation with anonymity. It'll be cool to see where that goes. So to recap, mesh networks have fundamental scaling limitations, both practical ones and theoretical ones. Weird-looking equipment gets you arrested. So watch out for it. And we have to consider anonymity just like confidentiality when we're building one of these systems. So to wrap up, this is our proposal for design objectives for future Dissent networks for circumventing large-scale communications blackouts. They need to be resilient to disruption, have meaningful scalability properties, be built from the components that aren't going to get you in trouble, and finally resist tracking by government adversaries. And we acknowledge this is a hard problem. There's good work to be done, and we hope that by presenting this, we're going to help people who are designing these systems now in the future. So if you have any questions, I'll take them now, or you can get in touch with me. Thanks.